All right. Hi, rock stars. This is Ben Chung, and he is here to give us a technical perspective on what AI is and how it works. Ben is an engineer at Nokia, and he is one of the smart people I know and a good friend. So, with that, I'm going to turn the mic over to Ben.
Right, welcome. So today I'm going to give you an overview of artificial intelligence and machine learning. I'm really honored to deliver this lecture. And I've been doing it for a number of years, as Becca knows. And it's really quite amazing how fast and how much progress AML has made in the past few years. So just a little bit more about myself. I've been in the wireless industry for 29 years, starting with 2G, CDMA and TDMA, and moving on to 3G, 4G, 5G, and now 6G. I work in standards, the Open Radio Alliance Network standards, which defines basically how wireless works in 5G and 6G. I have a number of patents. Prior to that, I was working at General Electric Medical Systems as an ultrasound and MRI engineer. And I've done a variety of things, extracurricular and outside of work. Worked at Habitat for Humanity. I was an emergency room volunteer. My very first job in high school was a librarian. I've been a recruiter, a photographer, a teacher, a guide, a judge. I have a master's and bachelor's from Purdue in electrical engineering, a PhD in operations research from Walden, and I've been to 31 countries on 6 continents. I'm trilingual. I've written 6 books, and the latest 2 of which are the periodic table of ideas and the elements of thinking. And I've published a number of games and was a former HeroClix world champion. Okay, so today I'm going to go over first an overview of AML, some of its key concepts. We'll dive into some key machine learning methods and a little bit of a timeline and history where we've been in AML, and some of its applications and some of the big players. So first, what are the big ideas? What is artificial intelligence? It's a big buzzword nowadays. Artificial intelligence are programs and machines that learn, reason, and make intelligent decisions. Machine learning is machines that are able to learn through experience without explicitly programming step by step everything that it does. So it's dynamically learns. And I'm going to touch on agentic AI. I'm not going to go too deep into it, but you should be aware that this is a big upcoming thing. It's very recent in the past year, really. But it's agentic AI is AI that acts autonomously in complex environments. It can make decisions and even create content without human oversight. And there are stages of artificial intelligence. We're basically in this artificial narrow intelligence stage, or what's called weak AI, where we have expert systems. Everything is algorithmic. There's a lot of data mining, pattern recognition, computer-human partnerships, and navigation systems like GPS or Waze is kind of an example of that. But we are pretty quickly and scarily quickly approaching artificial general intelligence, as you see with agentic AI here. Things that can recognize, things that can learn, things that can see, things that can process language. So maybe 10 years ago, these things were really just totally inconceivable. And today you're like, yeah, I can see an AI program that can recognize, that can learn, that can see the world and interact with its environment, and that can process language. This is ChatGPT, right? So we're pretty much kind of on the cusp of artificial general intelligence. And then uh, a loftier tier is artificial superintelligence, or ASI. It has transcendent ability, so it can innovate, it can be creative, it can imagine, it can decide, it can plan, it can forecast, and it's usually expressed through robotics and communications. And we even see some tendrils of these aspects as well, right? So an example of artificial narrow intelligence is something like Bard or ChatGPT or Echo or Alexa, Luna, Petbot. There's lots of AI sort of like pets now. I just saw one in the store the other day. Um, Artificial and general intelligence, some examples are like Wally or C3PO. something that can see, learn, and engage dynamically with its environment. And you can imagine like Luna is not far from Wally, or C3PO is just Google Translate on legs, right? So we're kind of there to some degree, right? Artificial superintelligence is something that can be aware. Maybe it poses something like, "What's the meaning of life?" And those are seen in sci-fi at the moment, like things like Megan or Mithrigan, Data or David from AI. Okay, so let's take a step back for a second, and let me try to step you through how does AI ML work at a 10,000-foot view, at a big picture view. How does it work now? And I say now because this is kind of just one way it could work, right? The when we see AI, when we say AML, or when you hear about artificial intelligence and machine learning, it's really kind of lowercase a, lowercase I, and really big letters M and really big letters L. So a lot of what we do now is still machine learning for the most part, but really advanced machine learning, and we're putting it together in lots of new and interesting ways, and we'll see here in a sec. So the first thing you need is some kind of problem to solve. So artificial narrow intelligence and artificial general intelligence generally has some kind of goal or some kind of problem to solve, or some kind of task to perform. So that's the first step. And then once you have a problem to solve, you're gonna collect some kind of data related to that problem. Suppose I want to sort pictures or make a sense of a vision field in front of me. I'm going to need raw input, and both quality, a lot of it, and quantity. High value data. Not all data is the same. I'll have to clean and format that data before I train my model so that it's meaningful, and then I feed that into my model and I'm training it. So the first part is about really collecting the data. So think when you're solving a problem, you're going to need information about that problem. Or say the problem is to walk across the room, right? A vision kind of problem, vision recognition, which is crucial in, say, something like a self-driving car. It has to recognize what's a person, what's another car, what's a street, what are the what's a stop sign. And in order for it to learn that, it has to see lots of pictures of stop signs, or see lots of other cars, see lots of other pictures of people. It needs raw input, and then it has to train in order to get better at learning those objects. So next, there's some kind of algorithm that is at the heart of how everything works. So it's going to find certain key characteristics and patterns from the raw data, and you're going to process everything. You're going to crunch everything through some kind of algorithm, and we'll talk a lot about those. And as a result of that, it's going to have some kind of output. It'll have some kind of updated model, or some kind of uh, uh, trained numbers that it uses to improve its operation. And there's different kinds of learning. We'll talk about that: supervised, unsupervised, and reinforcement. And then finally, of course, the point of all of this is it's going to make some kind of prediction. So do I need to turn left? Do I need to stop the car? Do I need to turn right? Or if you asked it something like in a chat bot kind of thing, it's going to spit out some kind of answer. And then it'll evaluate. There's some ways, particularly when it's training, to see how good it did, right? Of how useful was its output. So now you bear in mind that this framework uh, is really key to everything else pretty much that I'm going to talk about, right? So things take in data, they ingest data, they work somehow. There's some gears of how this thing works, or by some algorithmic form, and it's going to spit out some kind of decision and prediction, and it has to have some way to evaluate itself. Okay, so we'll talk about some key machine learning methods here. And the first thing we'll talk about is unsupervised learning. So think of basically building using Legos to build something, right? So it's unstructured, and there's lots of different ways that unsupervised learning can work, and we'll touch on some of these, like clustering on unlabeled data sets, dimensionality reduction, clustering, and big data visualization. Another is supervised learning, where basically there are labeled data sets. So humans, people, label the data, and then the algorithm trains from that. So classifies the data. You can use regression and forecasting and prediction. And then semi-supervised learning is kind of a combination of those. So think of like a teacher. So Becca is a professor, and she'll walk you through certain things, but then she'll expect you to do certain things on your own, right? So that's kind of semi-supervised learning. So there's a mix of labeled data, so there's some supervision, as well as free-form data that the machine has to make sense of. So there's both labeled and unlabeled data. In other words, some directed information, targets and non-targets, categories and examples. Um, so a teacher may show you some paradigms, some theories, some structured information, but also has free-form information for you to learn and think of like an exam. So things that you've never encountered that you have to kind of figure out on your own. And then there's a reasonable label cost. So if I have to, for example, if I want to sort, if I want an algorithm that can determine a picture of whether what you're showing me is, say, a cat, um, in an example of unsupervised learning, I might I might just have the algorithm just run off by itself, and eventually, hopefully, it figures out what a picture of a cat is. With supervised learning, maybe I take a million pictures of a cat and have people, maybe not a million, right? So people label 10,000 pictures of cats and say, these are pictures of cats, and I feed it into the program. And with with semi-supervised learning, maybe of the 1,000 pictures it trains from, I label 100 of them, right? So it has a more reasonable label cost. And then finally, there's something called reinforcement learning, and here think like carrot and stick is probably a good mental picture of what reinforcement learning is, right? So it makes real-time decisions, it acquires skills, and it can learn. So an example of supervised learning here on the left here is I learn specific, I feed it specific data sets. So if I want to try to have it recognize the picture of an apple, I label 1,000 pictures of an apple and say, and feed to the algorithm, here's pictures of apples. And surprisingly, actually, all those pictures of that people upload to the internet on cats, like all those cat spoofs and cat videos, and with their pets, that was rich data that early AML algorithms data mined that learned from. So on the right here is unsupervised learning, where basically the algorithm finds hidden patterns and groups data to identify clustering. So and there's no drive necessarily. It's just simply labeling the data as best and what it thinks are groups, which can be very useful. In semi-supervised learning, we're going to use both unlabeled data, so just a bunch of fruit, for example, and partially labeled data. So, I actually put labels. This is an orange. This is a banana. This is an apple. And then the machine learning model takes that in, and when it encounters a new piece of information, like this red apple on the bottom here with a question mark, it outputs here's an apple. Or another example, maybe I want a face recognition to recognize a celebrity, like Tom Cruise. I'll feed it a zillion pictures, and I'll label maybe 10, 20, 30, 40, 50, 100,000 pictures of Tom Cruise. That's an example of semi-supervised learning. In reinforcement learning, a good example of this is maybe um, something that can run through a maze, right? So here, I'm trying to get to the end of the maze. Maybe I have a virtual mouse that wants to run through the maze to find some cheese. And its reward is is finding that cheese, right? The environment is the maze, and I can take some kind of action, move forward, turn left, turn right, it can learn to do that particular action. Okay, so we're going to talk about some algorithms or some methods here for ML. So a priori association, K-means clustering and artificial neural networks, for unsupervised learning. For supervised learning, linear regression, support vector machines, decision tree classification, semi-supervised learning, general adversarial networks or GANs, self-trained naive Bayes classifiers, and for reinforcement learning, model-based value estimation and Q learning. So a lot of esoteric sounding titles and stuff, but I think when I step through some of these, it'll make more sense. I'll try to keep the math to a minimum and try to focus on kind of what the key ideas are here. So in a priori association, a priori means knowledge beforehand, right? So basically I'm trying to figure out, given some amount of knowledge before, what's the likelihood that something will happen, right? Kind of like how Bayesian statistics works. So an example of this is like a video recommendation system. So, for example, if you watched Marjorie, the movie or read the play Marjorie Prime, given some a priori knowledge that of that, or the movie Wall-E, what's the chance that you'll like, one or the other, given that you've seen something before? So, in the green are people who've seen both Wall-E and Marjorie Prime, and in the blue, people who saw Wall-E, and in the yellow, say the total number of users who haven't seen either. So you can basically there's something called a support, confidence, and lift, which are basically the support are the elements of one particular quality, say, for example, X that you've seen one of the movies, over the total number of elements. Let's say there's 100 users, 100 streamers, 100 people that have watched something. And the confidence is that elements with both X and Y, so people who have seen both the movies, over the elements of just X. And then the lift is the the confidence that over the support. So basically the gist of this idea is to figure out, given some prior knowledge, can I predict some future? Can I create a trend, right? So calculates the support and confidence, takes a subsets of items, and calculates to try to improve the lift. And again, this is how video recommendation engines work. Another method is called k-means clustering. And here, if I look on the diagram on the left here, I got a bunch of data, right? And imagine them, they're kind of like on a graph. And the blue, red, and green dots are basically are going to be these clusters. So data can sort of cluster around that data. So what I'm going to do is I'm going to calculate how far sort of a distance behind all of these other dots, these other data are away from that cluster. So, and there's various ways to kind of figure out the distance, but maybe a simple thing is, geographic distance, right? Latitude, longitude, altitude. So maybe I want to figure out what are the biggest population centers in a country, right? So maybe I might have a kind of distance from a sort of gravity center point, like maybe Washington, D.C., or San Francisco or Chicago. And to these other cities, I'm going to calculate a distance to those center points. So you can think of these centroids, but it can be any kind of data, right? So I just have to be able to represent some data in some vector, in some set of numbers, and then from there I can just use simple mathematics to calculate the Euclidean distance between things. And so this k-means clustering is I partition a number of observations into a k number of clusters into these blobs called Voronoi cells. Now, artificial neural networks is kind of complex, so it is a method of machine learning, but it's a really rich form of machine. There's lots and lots of stuff that's happened here. And fundamentally, it's basically kind of like you might think of your brain as a neural network, right? And early artificial intelligence research, and we'll get into the history of AI/ML in a second. Try to model the brain, try to see if the brain is pretty amazing. What if we try to model it using what we understand of axons and neurons? And that really spawned a lot of, and continues to drive a lot of the AML research and methods. So there are autoencoders that learn to code unlabeled data and copies it from input to output. Recurrent neural networks um, use basically feedback, and it takes the output and feeds it back in. And feed forward neural networks takes a direction of information between its layers, and that moves in one direction. So both of those use makes sense, right? You're taking you've taken what you've learned and seeing, how well it works and feeds it back. Convolutional neural networks are really good for visualization type stuff, like recognizing vision. And it can look at where there are sharp sort of edges, and and learn and sort of encode those edges. And it's good at detecting like smiles, eyeballs, noses, features of things, because it's looking for those edges. And now we're going to move to supervised learning. So here again, in supervised learning, I'm given some, I label stuff, and I have data points that I've labeled, and I give it some kind of training data set. I've labeled 1,000 pictures of cats. I feed it into this algorithm, and then out comes some kind of prediction, excuse me, and some kind of actual output, and I can compare that through a fit line. So um, so I have basically data that I'm working with, and I can create basically a best estimate line off that data. So if I'm trying to figure out um, pictures of a cat, and how far off was I, if I captured the cat quality in a set of numbers, how many whiskers does it have? How furry is it? And what its eyeballs and ears? And does it have pointy ears and so forth? And if I were to basically capture that aspect of the cat in some numbers, I can basically figure out how far off from this average, this line of regression that I am. And if we take that to another level, support vector machines are kind of similar to that, where basically I have certain features that I've captured and call those as dog features or cat features, and I'm specifically kind of teasing this information about capturing characteristics in sets of numbers, because I'm about to talk about large language models, and that's a really, really key concept to large language models. So I might, for example, have, like I said, how much fur this thing has, or how the shape of its eyes might be captured in a number, or the number of whiskers, or certain the pointiness of its ears, or how many legs and tails does it have, and that kind of thing. So I capture the catness of something in a set of numbers, and then from there I can basically figure out how far I am from particular lines, right? So here all the little red dots are class 1, all the blue triangles are class 2, in other words, they're dogs, and class 1 are cat features, let's say. And somehow at some point I'm going to take that new data, that new thing, like the picture on the left here, and it says this new incoming data, where does it fall? And when I calculate it, ideally, it should be a red circle, right? It should kind of fall towards the bottom right of this diagram. And if it was a dog, it'd fall more towards the upper left, right? And the separation, there's got to be some point where, what if the picture it's kind of like a dog cat, right? It's a very doggy looking cat or a very catty looking dog. So that's going to kind of fall right on that separating line, that what's called a separating hyperplane. And I'm able to, maybe it's harder to make a decision on that, right? And to calculate, to determine, to create this separating hyperplane, I basically figure out the sort of distance between the two separating things. And again, remember, this is supervised learning, so it's going to calculate through, it's going to take a look at all the data, and that you've told it these are cat pictures, you've told it these are dog pictures, so it can calculate this hyperplane. And it has multiple hyperplanes based on the things you want to separate. So maybe you also want to figure out pictures of cows, apart from dogs and cats. One of the more intuitive machine learning supervised methods is a decision tree. So it's kind of like playing 20 questions, right? So is this thing that I'm trying to classify, is it alive? No, it's not. And does it fly? Yes or no? No, it doesn't. And does it carry people? No. Does it carry more than 10 people? If so, it's a bus. If not, it's a car. So, so this sort of going from a root to a node to some sort of classification, by asking a series of sort of yes or no questions, is this decision tree method. Next is we'll talk about semi-supervised learning, and this uses what's called general adversarial networks. It was developed by Ian Goodfellow in 2014, and it utilizes two neural nets that kind of play off each other, a generator and a discriminator. So I pit essentially two AML algorithms against each other. One tries to fool the other one, and the one is the one I'm trying to train. So suppose again I'm trying to figure out pictures of dog dog pictures, whether they're real or fake dog pictures. So deep fakes are a thing nowadays, right? So here I have a generator that's trying to fool the discriminator. The discriminator is the actual algorithm I'm trying to train, and I have another algorithm that's trying to fool the discriminator. So here it generates a virtual picture of a dog, and the discriminator says, "Oh no, that's a fake," or identifies it as a picture of a real dog, of a real dog face. Another semi-supervised method is called self-trained naive Bayes classifier. I know that's a mouthful, but essentially, this is using Bayes statistics. And we'll see in the timeline here, Bayes inferences is a really, really powerful, one of the most important pivotal statistical things in that's relevant to AML. So it's basically saying, given that I have some prior knowledge, right, the Bayes theorem in the upper left here, given that I have some prior knowledge X, what's the chance of H happening? So, so given that I've seen before that clouds, that there's clouds in the sky, and what's the chance of rain? And we intuitively kind of know, well, there's rain happens when it's generally very overcast or very cloudy, right? So you can predict the chance of H happening given that something X has happened already, right? So here, here's an application where I'm trying to separate spam email from normal email. So something your browser like Gmail or Hotmail or whatever reader you use is an application, might be an application of this. So here we look like, if we see an email, dear love, I'd like to discuss something at lunch, and I have $1 million to deposit into your bank. So if I see these words, dear and love, dismiss and lunch, $1 million and bank, what's the chance that it's a spam, given that I see that word? Well, if we just look at dear for a second, so the chance that we see dear in the word spam in spam emails is kind of low, but the chance that we see dear in a normal email is pretty high, right? So given that we've seen the word dear, what's the chance that this is spam email, or what's the chance this is normal email? Well, you don't often see the word million in normal emails, but that Nigerian prince scam, maybe you see it a lot when that was going around. You might see that word a lot. I happen to have $1 million to deposit into your bank if you'll just give me your bank account. So you'll see that word. Given that I see that word, there's a higher chance that it's spam email. And that's kind of the idea behind this self-trained naive Bayes classifier. It's utilizing Bayesian statistics, or the Bayes theorem applied to machine learning. Okay, next we'll talk about reinforcement learning. So model-based value estimation, again, the reinforcement learning is driven by I have some kind of environment and I'm doing something to that environment. I take some kind of action and that gets me to some kind of state and I compare it against some kind of reward. So think of like a algorithm that can learn to play a simple car racing game, right? I can accelerate, I can decelerate, I can turn. So I have some sort of agency, I have some sort of actions I can take, and I have some sort of states. My car's currently on the road, I've crashed, and I have some sort of reward. I've got to, I've gotten through the first lap, for example. So it's basically it's a model-based method. It uses a Markov decision process, and a a Markov chain in statistics means that what's happened before uh, doesn't affect what's happening right now, right? Like the each moment is statistically independent of the next event. So, but a Markov decision process is I'm looking at the chance of things transitioning in a state machine from one thing to another. Dynamic programming, so it breaks down the problem into subproblems, and that's a recurrent idea we'll see later on as well. And it uses Bellman optimality to recursively optimize a subproblem, and then it iterates. So there's a lot of math here I won't go into, but basically, just remember, basically, the reinforcement learning is think of like the car it's in some kind of environment. The little mouse is running through some kind of maze. Um, I can take some set of actions, turn left, accelerate, decelerate, and through those actions in that environment, I observe what happens. I've crashed, I'm still on the road. And I may represent where I am with some sort of states. So maybe I represent the state of the vehicle, um, maybe that the engine is hot, the engine is cold, the engine is overheating, that sort of thing. And then I have some sort of reward. Did I make it past the first lap? Did I make it around this curve? Did I make it around this corner? And from that, I can essentially learn to play this very simple game. Now, this reinforcement as learning is used in like video games, right? It's used. It's how video games can play off of a human, and it provides a challenge for us. So another is Q learning. So Q learning is similar. It uses it's a similar in concept in that it's a reinforcement learning. It takes some kind of action. There's some kind of states, and after it takes some kind of action, it observes what happened in the environment. It takes some action in the environment, and it has some sort of rewards. So, for example, an action might be in a chess game. It might make a move in chess, and then the states are there. Might be the board states, and the reward is maybe I've captured a piece, or maybe I've won the game. I've got the king in check or checkmate. Or suppose I'm playing Mario Brothers, and I have Mario can take some sort of actions. He can jump, go left or right, and the particular state is the state of the game. So similar sort of idea to the previous thing we saw, but this is again just a way that systems can learn, and it's been used in things like AlphaGo and Atari's DeepMind AI. Okay, so I'm gonna next talk about large language models because in 2022 it kind of exploded on the scene, right, with ChatGPT 3.5. So large language models use deep learning to analyze text, to understand and generate language, and it's trained on a diverse data sets to predict and produce text. Now, it's expensive to train it can be millions and millions of dollars to train a large language model, but it's pretty amazing. As I'm guessing that most of you have tried some sort of chatbot or large language model like such as ChatGPT, and so I'll kind of walk through at a high level at least, kind of how it works. So a really key insight was this 2013 project by Google called Word2Vec. And Word2Vecs are a key building block for how large language models work and how they encode relationships between words. This is super not obvious, but really pivotal to how large language models work. And So I'm going to represent a word with many numbers, basically. Right? You might think, well, why not pick one number to represent it? But we'll see in a second here that it's going to take each of the words in a sentence and vectorize it. Now, machines are really good at using numbers to do stuff, right? And they're not maybe not as good intrinsically with language or walking across a room, right? But they're really good with numbers. And the key insight is I can take a very complex thing like language and decompose it into basically a set of numbers. So I use a bunch of numbers to represent king, queen, man, and woman. Next, I need to consider context because words can have multiple meanings based on context. Language is kind of complex in that way. So word vectors are used to help determine the meaning. So one of my favorite phrases here is like time flies like an arrow, but fruit flies like a banana. And now you can understand that relatively easily, right? Like you'll understand that time, like a clock sense of time, um, moves quite quickly. Like it flies in a straight line from past to future. It flies like an arrow. You can understand that phrase. But fruit flies, like the little insect, they like bananas. They like fruit, hence the fruit flies. But you can understand naturally. Your mind naturally understands because you've trained your mind that oh, when I see a fruit fly, even though I saw the word fly, so it's sort of an indicator that I'm talking about directionality, like an airplane flying, for example. And an arrow, like a bow and arrow. So I've triggered your mind to think of something flying through the air like that might be flown by an arrow. But then when you come across fruit flies, the first thing you'll do is apply, oh, it's like something flying across the room, like an arrow. But in this case, it's not. Fruit flies have to be put together, and in context, it's a thing, and that thing likes bananas. Or how about flying planes can be dangerous, right? So do I mean that an airline pilot, a pilot that's piloting an airplane, that's a dangerous activity? Or do I mean the object that's moving through the air very quickly? What happens if it crashes? That can be very dangerous, right? So is flying planes, is the act of flying planes, as in a pilot flying a plane, is that a dangerous activity? Or do I mean here that uh, heavier than air object propelled by an engine could be dangerous if for example, if it happens to crash. And we people we figure out what sense you mean by the context of what you've been talking about, or the context of the paragraph, or the context of the conversation. And LLMs have to do the same. So next we talk about transformers. So in 2017, Google introduced a neural network architecture using transformers, where each layer in a large language model is a transformer. And these layers figure out context and meaning by updating word vectors. So for example, John wants his bank to cash his check. So each of the transformers figures out certain aspects of the sentence. And that's part of the numbering here that's important. So we find out that wants and cash can be verbs here. And I run across a pronoun, and what pronoun is that really referring to? And what are the objects that I'm talking about? So layers of transformers figure out both the context and semantics and lexicon, and that's how it's able to work. Um, so each of these attention steps is called um, has some matchmaking service for the words. So for example, I want to match pronouns with nouns. I need to resolve homonyms, and I need to link two-word pairs. So that's an important aspect of figuring out the meaning of a sentence. So I may have a query vector. So I just ran across the word his, and now somewhere in the sentence there should be a noun, some kind of male person in the sentence. And is it John? Is it some kind of name? Is it a common word for a name or whatnot, right? So ChatGPT 3 had 96 transformer layers, and ChatGPT 4 has 120. So they have different various attention objectives. Um, so there's lots of different transformer layers that help figure out certain aspects of language. So I look at the lexicon, I parse the syntax, I look at the meaning, the semantic analysis, I figure out kind of the discourse, what you're talking about, and then the pragmatic analysis, how on target was this, how pragmatic was this thing that you're talking about. So, and then what comes out of this large language model is basically just a word. So, and I keep running it through this and keep going through the output and I walk backwards and feed it through the network again. And through each epoch, through each phase, um, through each time of training, it gets better and better at figuring out what the meaning was. So I know that's maybe a lot to digest, but I think the key insight here is that large language models work by basically assigning lots of numbers, each a dimension, to a particular word. And one of the layers of the model figures out, oh, I saw the word king, and that's often kind of related to the word queen, or I saw the word man, and that's often related to the word woman. And so it can find out the sort of distance, or it can find out things that are related to each other because of the way it's decomposed and assigned numbers to words. Okay, so um, uh, AI is moving at a breathtakingly fast pace, and in 2020 to 2022, ChatGPT 3 kind of exploded on the social consciousness. Everybody has now heard of a chatbot, of a large language model, of ChatGPT 3, and many other chatbots followed suit. And AI agents were sort of the next thing that came about. Now, you might not have heard of AI agents yet. They're not so prolific yet. I've used AI agents at my work, and they're really pretty amazing, right? So depending on where and when you get to use them, they're really neat. But let me try to explain. Let me try to give you an example so that you understand what they are. So AI, we start first with AI workflows. So suppose I want to program something in my calendar, or suppose I want to come up with a daily exercise regimen, or suppose I want some kind of program to figure out my meals so I can eat nutritionally, right? Um, I can create some sort of workflow to make that happen, right? So step one is I need to go grocery shopping. Step two is I need to figure out, I need to plan, um, 21 meals in the week, and what ingredients do I need? And step three is, what's the nutritional value of those ingredients? So there's a certain flow, there's certain steps in making that happen. And in an AI workflow, I have some predefined human procedures: buy groceries, make dinner. And I pair that with now, I can pair that with external tools to help make that happen, right? So you might hear the term RAG, or retrieval augmented generation, um, and that plays into basically making this flow, this procedure, this step-by-step thing happen. And if I add reasoning to that, so AI agents can then replace the human in the workflow. So suppose I have to manually crunch the numbers to figure out how many, I don't know, how many calories or how much saturated fat is in this set of 21 meals I ate, and that sort of thing. I can use reasoning to replace that with an AI, and and I have a bot to evaluate it. And there's lots of different AI agents I'll talk about in a second. So so I have an AI agent. So if what I just talked about with large language models and Word2Vec, et cetera, is one Lego block, AI agents are kind of building using lots of those Lego blocks to do something more meaningful, right? So, and LLMs are restricted because they don't know environmental information. So, for example, um, suppose in this example I created, it's a calendar management thing, appointment scheduling agent. So its purpose maybe is to streamline your calendar or to respond to, hey, I'm available for this at this time or that time, or I'm not available, or lots of emails going back and forth when we're trying to set up a meeting. So it's kind of streamline that task. So I have the goal to manage your calendar. Well, a basic simple LLM like ChatGPT doesn't have access to your calendar. It doesn't know what meetings you have. It doesn't know that you have a meeting, at 9 a.m. on Thursday. So, however, AI agents can, right? So they use a collection of, they may use a collection of partner LLMs in figuring out how to accomplish a particular task. I may express that I'm trying, what's the intent? What are you trying to do, right? I'm trying to optimize my calendar. I'm trying to schedule, I want to schedule an auto maintenance appointment. I want to schedule, an appointment to service my home or service my car. Um, I need to decode the intent, and it can represent, just like in the reinforcement learning, it has internal states that it can represent, of maybe a one state might be the level of order that you have in your calendar, or the amount of fullness that you have in your calendar, or that kind of thing. And it has some external knowledge. It can schedule an appointment. It has an AI agent isn't just on its own little bubble, just trying to answer questions off of the internet. It can actually do stuff. It can that are meaningful to you, right? It can interact with, say, for example, your calendar or some sort of other personal app, right? So maybe it has knowledge of the state of your car. It needs service. It's gotten, needs an oil change, or it has this much gas, or whatnot. Or if I want to try to have an automated grocery thing, it has to know the level of milk you have in your refrigerator, or cheese, or fruit. So it interacts with the environment in some way. It interacts with your environment in some way, a personal thing that transcends a normal LLM, but it utilizes other LLM bots. It uses other bots to figure stuff out. And of course, just like any good AI thing, it iterates, it gets feedback, it optimizes and learns and gets better over time. So that's one thing you have to bear in mind the first time you work with an AML thing, whatever that is. It won't necessarily be great. It may have to adapt and learn and get better, just like a baby learning to walk, right? Like you can't, we have these, sometimes I run across people and have conversations, like some people, they get so hyped about reading media or articles or whatever, and they kind of have too lofty, too unrealistic goals of AML. Even though it's advancing at a breathtaking pace, it does need to be trained. It does need to learn. And again, training like ChatGPT takes millions and millions of dollars. It's not simple or easy or fast to train things. And the training is sort of garbage in, garbage out. It's only as good sometimes as the data that you're training off of, right? So you have to bear stuff like that in mind. So the output is that you have some updated streamlined calendar. You've got tasks scheduled, and you synchronize entries. So I mentioned here there's lots of different kinds of AI agents, and let me next talk about some of these different kinds of AI agents that exist. So the simplest is it's called a simple reflex agent. It's just basically if some condition, then take some action. So it's good for very predictable, observable, very well-known, very sort of narrow tasks, such as interpreting sensors, or having robots walk in a line, or like cars platooning, following each other, or like fixed chat, FAQ chatbots with fixed canned responses. Next, model-based agents you can utilize past information. It uses historical information in order to keep an internal state of something that you're interested in. So maybe you've had many calendars, you've had many lunches with your friend Jim, or you want to remember your mom's birthday, like that kind of thing. So past information helps it decide what to do. So examples are smart homes, warehouse robots, inventory tracking systems. Another is goal-based agents, where basically it's trying to reach some sort of goal. It has to, it's very, all of its actions are trying to hit some kind of target, right? It could be used for routing, think like, GPS system, or logistics planning might be an AI agent that maybe helps you plan a party, or it can play a game, or have some kind of objective-based decision problem that's trying to solve. Utility agents maximize utility like in the economic sense. So there's some kind of trade-off it's making. There's some kind of actions it's meritoriously finding the best among those actions. And it's kind of like puzzle piecing different things together to figure out what works best, what's the best use of resources. Maybe there's an opportunity cost for certain actions. So in the calendar example I gave above, maybe you have, just in real life, you have all sorts of things that claw and gnaw and compete for your time, right? Attention is one of our most precious resources right now in this information overloaded world. And everything you do has some kind of opportunity cost. You go to the movie, you read a book, whatever. Everything you do has some sort of time cost to it, right? So here, these are all examples of things you want to maximize, find a overall utility to. I want to manage your portfolio, for example, stocks, or I want to allocate some kind of resources like money, your savings, or I want to schedule a calendar. And I can trade off things like cost, risk, speed, and other trade-off criteria. Learning hierarchical AI agents, I know that's a mouthful, but basically, it's an AI agent that can learn. That's pretty simple, right? And it's an AI agent also that is I mentioned before, a one an LLM is just one Lego block now, right? We've moved kind of on from ChatGPT, believe it or not, in just a couple of years. So now we're talking about sets of LLMs, sets of agents that work together to do something. So, and those are called hierarchical agents, right? It breaks a big task down into littler tasks, more manageable tasks. And I have some higher level controller that can kind of coordinate these lower level things. So, it can learn to, just like riding a bicycle, these learning AI agents learn, or like learning to write, they get better over time doing something. But I might also use a confederation, a set of collaborators to a set of other bots to do stuff to make it happen. And that leads us to multi-agent AI systems where that again use several agents together. I may use not just bots, but maybe multiple agents together to cooperate and compete in some sort of shared environment. So a much more then these can solve much more complex systems like smart traffic management systems, robotic swarms, like think drones, and distributed systems. So let's tie all this together, right? So we started with kind of chatbots. We talked about neural nets. We talked about deep learning and machine learning. Those are maybe those are the fundamental Lego building blocks. We put those together and we can create something pretty amazing. An LLM is just a specific kind of neural net that if you happen to tokenize words into a bunch of numbers and use transformer layers, and you can do some pretty incredible language magic. And from that, we have basically various forms of large language models that do different things. So you can have the simplest is like chatbot, like ChatGPT, but there's more advanced ones like things that are support bots and social media bots, assisting bots, and robotic process automation (RPA) bots. So things that are essentially use that same sort of idea of a large language model, but in different arenas. So uh, that's a that's something already quite amazing that took the world by storm in 2022 with ChatGPT 3.5. And now, what if we put sets of those together? What if we put multiples things of those together? We can do even more amazing things. So we talked about AI workflows, where basically I have some sort of procedure that I'm trying to accomplish. Those have some sort of steps, but a human is still involved in accomplishing those steps, planning your calendar, grocery shopping, etc. And now I can take a set of these bots here, and I can apply them to try to solve workflows. So workflows can be pretty complex, right? Like think of machine, factory manufacturing or whatnot. They can get pretty complex. And so I also use a bot that's one of these kinds of bots that's good at evaluating how I've done. And we've talked about AI agents. And now the latest thing is called Agentic AI. And agentic AI, I'm not going to go into this in too much detail because agentic AI is a lot more theoretical, but it's also very powerful. There are lots of protocols that agentic AI is based on. So you might hear the term MCP, Model Context Protocol, or Google's A2A protocol, or the agent communication protocol, or the agent network protocol. But a lot of these protocols set the stage for basically an internet of agents. So agents that can work together, that can collaborate, these multi-agentic solutions. And there's agent development kits. And these all basically are ways that we can take one Lego building block, put multiples of those Lego building blocks to say, piece together a more complex thing, an AI agent, and I can take multiples of those and create even higher level constructs, and we call that agentic AI. And that's starting to be a lot closer to AGI, artificial general intelligence. So it's autonomous. It's characterized by being autonomous, adaptive, goal-oriented, self-evolving, reasoning. It can pursue goals dynamically and decide and decision making, right? Those are qualities of an AGI, right? So you see the stepping stone of something that we're building from something simpler to something more complex to something even more complex and towards AGI. It's palpable. Okay, so where are we? So far, we've talked about artificial narrow intelligence. We've talked about artificial general intelligence, artificial superintelligence, things that can programs and machines that can learn, reason, intelligent, and make intelligent decisions. We've talked about the various forms of machine learning and the various kinds of machine learning, different methods and techniques for unsupervised, supervised, semi-supervised, and reinforcement learning. And we've also talked about agentic AI, AI that can act autonomously in complex environments, make decisions, and even create content without human oversight. So we talked about those are driven from the various AI protocols, agents of frameworks, and an internet of agents.